Hi, so welcome to the first videos for the practice. We're going to start coding and seeing how to resolve groundwater storage with Grace. So first off, we're going to start with section 1. Very smooth. We're just going to explore the study area. So to properly evaluate changes in hydrologic storage, you have to examine the changes happening in the hydrologically connected systems so that your assessment is accurate. So we want to look at the watersheds, the basins, the reservoirs, because the watersheds and basins are going to be areas where precipitation drains to a common point. And so we're going to use the watershed boundary data set to delineate first the drainage area for California's Central Valley. And using A2C codes, we're going to identify connected basins in the US. And then we're also going to find the reservoirs within the area. California has over 150 reservoirs distributed across the state. So we're going to start with the A20A, A21A checkpoint. And the best thing I would say is copy paste the checkpoint into a new script, which we're going to do. So I already have all the scripts prepared, but in this case, let's just focus on copy pasting checkpoint A21A. So first off, in the following sections of this code, we're going to load the 3 basins by their unique 4-digit HUC codes that I mentioned from WBD. Then once we've extracted them, we'll merge them so that we have one basin variable. And then using the filter, we're going to filter the basin variables by HUC so that we're really only extracting 3 to a variable basin. So as I mentioned here, we're using the codes and then we're filtering the HUC4 codes so that we can then map our basin for the Central Valley Basin specifically. So then after that, we want to map the extent of agriculture in the region because again, the reservoirs lead water to farms and we want to have an understanding of what the agricultural land is like, what the cropland land cover is like in California's Central Valley. So this will map the greatest need for where water has to occur and occurs. So first we have a variable land cover. We're going to find it by our image collection in USDA. So this is from a simple search. We're going to filter out the dates, look for cultivated. Again, we're going to add land cover to our layer, and we're specifically looking for cropland, but we've already kind of determined that. So you're just simply going to name it cropland and make it true so that it can appear. And then we're going to load our reservoir locations using our basin boundary that we just created to select the reservoirs that are within the boundary of the basin so that we can quantify changes in surface water storage from that. So that's using a reservoir index, and we're going to filter the reservoir by locations using the Central Valley geometry. So let's print that out. So what we get is 3 to 4 layers. In this case, it's only 3 because the trend is in the section 2, which we'll see after. So we have the Central Valley basins. Then we have our cropland, as we named right here, which we got from our land cover image collection, looking specifically at cultivated land. And then this is appearing as a deep purple hue. And then we have our reservoirs. So the reservoirs will vary in size and capacity and the regions of the state that they support. In Central Valley specifically, water conveyance infrastructure allows the transport of water from north to south. And using our basin boundary, we were able to select those reservoirs from California's Department of Water Resources Data Exchange Center, the CDEC. And if you're going to apply this in another study region, it's very crucial to acquire in situ surface water storage to then resolve that region's groundwater storage changes. So it's why it's important to look at this before we get into the GRACE and the groundwater. And so right now we're seeing the blue dots that are appearing on the map, and this is just giving the distribution of water storage across the Central Valley. And the water conveyance infrastructure and the natural rivers are going to deliver water to farms across the valley. Hence why it's important to also look at the cropland. And we're basically using the basin as our boundary. However, even with all these reservoirs, many water users are still going to rely on groundwater to meet their needs. And that's why it's so important for these gravity sensing satellites to exist, because if we're going to rely on groundwater, we're going to rely on this technology to find it. So now we're going to look at section 2 and look into how we can resolve the groundwater storage. Okay, so now we're going to move to section 2, and this is going to look more at GRACE and resolving groundwater storage. And that's going to be kind of spread out around section 2, 3, 4, and 5. So the first section 2, first part of it is tracking total water storage changes in California with GRACE. So we're going to look at section 2.1, which is going to be importing GRACE data, plotting changes in total water storage in California, and then section 2.2, which is going to estimate the linear trend in TWSA, total water storage anomaly, over time. We're going to be using A2.1 checkpoint for this section 2. And so you can go ahead and copy and paste into your new script. So we have section 2 here, starting at checkpoint H1B. So let's understand what's happening. So GRACE, as I mentioned, can directly track changes in TWSA. And changes in TWSA indicate which regions are gaining or losing water. Back in the other sections, we have the land cover, specifically cropland, we have our reservoirs, and we have the basin. So we've set up our central valley already. Now, what we want to do is TWSA is used to detect and monitor long-term hydrological drought. And GRACE, as I mentioned, is the tandem satellites. So first, we're going to import GRACE data and plot changes in total water storage in California. And you start by importing the image collection and selecting the proper band chart. So as I mentioned earlier, a lot of these you just put in the search bar here, and then you get the image collection that you require. So in this case, let's say we do it and we paste it in, we get the GRACE monthly mass grids. And so in this case, you get all of the metadata information on this image collection. You get the band information and etc. The band information is really going to be important because that's what you're going to call, which you've probably learned from the other chapters already, especially chapter 2 in the book. So when we mean select the good band, the band that you require, it's going to be the LWE thickness, which is the equivalent liquid water thickness in centimeters, which is going to provide you with information about the total water storage. So here is what's happening. So the equivalent water thickness represents the total terrestrial water storage anomalies from soil moisture, snow, surface water, as well as groundwater. And the time coverage for the monthly grids are determined by GRACE months. So after that, the GRACE data imported here has already been processed to provide units of TWSA. And so the data contained in this data sets are units of, as I mentioned, equivalent water thickness anomalies. And the GRACE hydrologic data is presented as anomalies because GRACE doesn't directly observe the gravitational pull of only water. It also includes Earth's surface. So before we start plotting it, to disentangle the signal of water, we can look at changes relative to a longer-term mean gravity signal. And the anomalies represent the difference between a given month's observation and a multi-year mean. So now let's plot it and see what happens when we want to look at the TWSA chart over time. So in this case, we're filtering from 2003 to 2016. So I'm going to go ahead and comment out this section so we can just run and get our chart. So your chart, as you know from other chapters, is going to appear in your console here. And then let's open it up and look at it. So as you can see, we've got on the left the TWSA on the y-axis, and on the x-axis you have your timeline. So what's happening here? As you can see, the seasonality and interannual variations in TWSA are represented by this chart. And then you have the LWE thickness here in this blue line. And if you look at winter months, so December, February, March, like let's say here, these reveal periods of maximum water storage because you've got snowpack, full reservoirs, and wet soil. Then you get into summer and early fall. Let's say we look here at June, July, and then we get into October, September, these reveal less TWSA because the snow has melted, the reservoir water has been used, and the soil is drying out. And additionally, the summer months are a period was when groundwater is extracted and used to supplement a limited surface water supply. So the evidence of drought emerged through declining TWSA between 2006 and 2009. So you can see this declining trend here, and 2012 to 2017. So you can see a major declining in the surface water here. Well, the water storage, sorry, in this chart. However, while you do get the TWSA graph using the monthly observations like this one, you can also aggregate into annual means to get a better sense of what's happening in the graph throughout the years, especially when you're examining times of drought in California between 2006 2009 and then 2012 2017. And what I mean by that is when we go in the first section here, in section 2, we're going to require this for section 5 to work. But basically, we're starting and ending the years to annualize the data. And this is what we call grace year here. And we're basically just mapping out a function in a loop in order to create annual means of the data so that it becomes more efficient to use. And you'll see why, just because once we plot the chart right here, you're able to see more detail per year, and you can see the declines in a more efficient way. So I already ran this. I'm just going to show you what it does. So now we're looking at the total annualized water storage anomalies. And as you can see, because we've created an annual mean, then we can just look at what's happening per year. And then we can see that from 2006 to about 2009, and then 2011, maybe more in 2012, there are some sharp declines in here in total water storage. So this is just to give an example of how you can manipulate GRACE data. And we're going to revisit this in section 5 when we compute more about the groundwater storage. So now that we have examined what's happening in the chart itself, in terms of total water storage from 2003 to 2016, we want to be able to see that on the map. So this goes to section 2.2, estimating the linear trend in TWSA over time. So now that we've got a gist of what's happening with the total water storage in the chart, seeing a decline between specific months, looking at which months will show a higher water storage, less water storage based on this LWE thickness, we want to see that represented as a layer on the map. This is what we're going to look like in the section 2.2 to estimate the linear trend in TWSA over time. So we've plotted the changes in total water storage in California. What does it look like over time? So in this case, it's still A2.1b, but here we're going to compute the trend, list the independent variables, name the dependent variables, flatten the coefficients, create a layer, set your visualization parameters, and add to the map. So here in general, it gets a bit more complex. I really recommend you going into the book itself to look at more information about the equations and what's behind what is being built here, because it gets a bit complex to explain just through this video, and it might get lost in translation. But the basic of it is that in chapter 4.6 in Earth Engine, we learn to fit linear models to time series data. And with unique linear fits for each pixel based on the values through time, you're able to then put this on a map layer. And the model that we talk about in the chapter specifically for A2.1 is the model behind the trend line added to the chart that we just created. So to fit this trend model to the GRACE-based TWA series, we can use the linear regression reducer. So in this case, this is what's happening here. We're computing a linear trend, and we're going to have two bands, residuals, and a 2 times 1 band called coefficients. So you've got the reducer linear regressions, you've got the coefficients, and then you have the information here to create a layer of the TWSA slope to add to the map. This is going to allow us to visualize the GRACE trends to capture the spatial scales on which GRACE can resolve TWSA. And as I mentioned often, GRACE is really good at capturing these changes only for larger basins. So once we visualize these GRACE trends, which will appear here, we'll have a bit more information about the basin. And so I'll talk about more of that once that appears. But I just want to mention that as you go through this code, really what you have to grasp is that while we've computed a chart, we want to compute a trend for each pixel because then we can map out the regions of most change. And so this is what's happening here is that you are collecting the information that you've already gathered, like the date, the start time, your dependent variables, your basin, you're filtering by bounds because you have to stay within the basin. And then you're creating your list of independent and independent variables because you're computing a linear trend that is going to be specifics to the map. So here in this case, the visualization parameters is just to allow you to understand what you're going to see. So you've got the positive blue and the negative red. So once I run that, this is what happens, is that here we have the blue that's going to be positive, and the red here is there's different shades of red, which means different things, but again, it's just showing the declining trend in total water storage. And so the slope layer is revealing that the Tulare Basin, so the southernmost basin in the Central Valley, experienced the largest negative changes in TWSA over the time period. And the time period in this case, 2003 to 2016. As I mentioned, there's different shades of red, right? So the darker red indicates greater negative change, and blue represents positive change. So this is a result of the region not receiving winter rain or snow and having the most junior surface water rights in the Central Valley. Now, in the next section, section 3, we're going to review how to unpack the TWSA signal to resolve changes in groundwater storage anomalies for the basin. So far, what we've done is collect enough information to get a general idea of the area. So we've got the Central Valley Basin, which serves as our filter bounds, our cropland, which serves as our information for where water is most important and is mostly used. And then we've got our reservoirs, which in the Central Valley is just giving an idea of where the water's coming from, where it's being sent to the farms. And then we have our trend, not only from our chart where we can really see and look at the different months, but also see throughout this timeline what's happening. And then translate this trend into the map layer itself by looking at the linear trend per pixel and using a color combination to look at the best areas and the worst areas in terms of total water storage. So now we'll move on to section 3 in the next video.